Dear friends and colleagues, I wish you very welcome to this webinar on modeling and integrated assessment tools for water-sensitive urban planning. This webinar is an effort of the IWA specialist group on modeling and integrated assessment. And we use this webinar series to highlight various aspects of modeling related to water issues. And this is the 15th webinar that we are producing. But before we go into the actual webinar, my name is Dr. Ulf Jeppsson from Lund University in Sweden, and I'm the chair of the MIA specialist group. And I just want to take a few minutes to say a few words related to our specialist group before we start the actual presentations. The MIA specialist group is, or at least we hope and try to be, one of the most active specialist groups within the International Water Association. And it is the group that is really focusing on modeling of all aspects related to water and wastewater, and in connection to other water issues as well. And it's open for everybody who is a member of IWA, and currently we have some 2,200 members in this in our group. We one of the most important ways that we work is through task groups. And task groups, that is a small size group of experts that are focusing on a specific topic for a few years, and then normally producing an IWA scientific and technical report at the end of the work. And we've had, as you can see in the list here, we have had a number of task groups, and 3 of them have actually finished very recently, within the last year, 1.5 years. And we still have 2 active task groups, the one on membrane bioreactor modeling and control, and one on a good modeling practice in water resource recovery systems. Many of the more recent scientific and technical reports are available open access, so you can download and read all the material that have been gathered in those texts. Another way that we work is through working groups, and a working group is often a larger group of persons that are promoting and investigating maybe a more general topic. And we have at this point 3 working groups active within the MIA specialist group. And finally, we have the conferences that are connected to the group. Those are the WRR Mod modeling seminars and the Watermatics conferences. I'll come back to those in just a few seconds. Speaking of scientific and technical reports, we have, I just want to promote this one, which is the latest one that was released or published just a few months ago. And that is the STR on physical-chemical modeling. We will actually have a webinar in May. I will come back to that at the end of our webinar, where the task group that produced this STR will give a webinar with their most interesting results. And speaking of conferences, if we look into the future a bit, we have some upcoming events of great interest, I hope. We have, first of all, the Watermatics 2023 symposium. That will be in the beautiful city of Quebec in Canada, 23rd to 27th of September this year. And there's still a possibility to submit abstracts for or extended abstracts for that conference for another 1.5 weeks before the deadline is reached. And that conference is organized by Peter van Rollegem and Elena Torfs. Well, Elena, I see that I have not updated properly. Elena Torfs is also at the University of Laval in Quebec nowadays. Then in 2024, we have our WRR modeling seminar series, the 9th of those seminars. And that is organized every 2 years. And the next one will be in Notre Dame in Indiana, in the US, in 6th to 10th of April, 2024. So we hope to also see many of you there. And then, since we want to look ahead into the future, there will also very soon be a call for potential organizers of the WRR mod in 2026. So everybody who's interested to take on such a task will soon have a chance to submit a proposal for that. The Watermatics conference, that they are given every 4th year, so the next one there will not be until 2027. If no one hear about what we are doing in the MIA group and what we achieved, then we hardly exist. So therefore we have a number of channels that you and others who want to learn more about our activities, you can follow news and updates from us. We have our MIA specialist group website on the IVA Connect system. Well, actually on the IVA Connect Plus system, as it is called nowadays. So that address that shows here is not absolutely correct. I will modify that later on. And that is open for everybody who's a member of IWA. If you're not a member of IWA, but still want to follow what the specialist group is doing, then you can use this open website that we also maintain, where everybody can get basically the same information as you get at the IVA Connect Plus website. We also have a LinkedIn account that you can follow and a Twitter account that you can follow. And we produce regular newsletters. Finally, we also have our own YouTube channel where we make webinars like this one, generally available for anybody who wants to listen in. So I just hope to see you all as members of the MIA Specialist Group, if you're not already a member, in the close future. And with that, I leave the floor to Dr. Natasha Atanasova from the University of Ljubljana in Slovenia. She will introduce the topic of today's webinar and be the moderator during the ongoing webinar. And I wish you all a great time.
Hello, everybody. Thank you all for this introduction and for inviting me to this webinar. So I would like to say first a few introductory words. Just let me share my screen. So the topic of today's webinar is modeling and integrated assessment tools for water-sensitive urban planning. So before we start with our speakers, let me give you a few introductory thoughts to the topic. So water-sensitive urban design is a set of principles, concepts, and technologies towards sustainable water management. So sustainable water management differs in three points from the water management that we are witnessing in most of the cities today. And these 3 points are that rainwater is not drained, but it is allowed to recharge groundwater, it is harvested, and it is allowed, of course, to feed green spaces. Wastewater is a resource that is being recovered and reused, and both of them, rainwater and wastewater, are alternative water sources, and thus they reduce the water demand if they're harvested, of course. They save fresh water resources, and which also this impacts the existing water supply systems. This kind of design has plenty of challenges. Cities are faced with plenty of challenges when implementing water-sensitive urban design, and this modeling can help a lot in overcoming these challenges. So basically, water-sensitive urban design can be implemented either sporadically by trial and error, and I'm sure many of us have seen this kind of implementation. Of course, we can build a rain garden, but then if it is not designed correctly, it may cause some problems. But this kind of water-sensitive urban design can be implemented by taking informed decisions, which are supported, of course, by models. Let me give you a short example on how to support decisions when implementing stormwater control measures, which are, in other words, elements of water-sensitive urban design. So in these few words, I would like to touch on the scope of the models of water-sensitive urban design. So basically, we always start with some kind of preparation, which is collecting data, defining the scope of our model, what do we want to model, and so on, which is followed by setting up hydrology and hydraulic models, which gives us a sense of the quantity of the water flows in the city and in the urban water infrastructure. Then, of course, we have plenty of options and tools to design the stormwater control measures or water-sensitive urban design elements, and we are using then these hydrology hydraulic models to assess their efficiency, how they fit in the urban space. And when doing so, we can use, of course, multi-criteria analysis. Multi-criteria analysis, and with this, we evaluate what is the best setting of our water-sensitive urban design. This is a really broad scheme, and each one of these elements has a number of sub-models and different modeling tasks. Only this one in the hydrology hydraulic models includes a huge amount of research work in optimization, calibration tasks, and so on. However, today we will focus more in this part, which is how to design, how to place these measures or elements. And today in this seminar, we will hear a lot about spatial planning submodels, how to optimize the placement of these elements, how to deal with the interactions between different users of the urban space, and of course to assess different design methods of stormwater control measures. Some of these elements are also rainwater harvesting at building scales and retention and detention-based stormwater control measures. And of course, we are interested when we are harvesting water, how they impact the water demand. And here we will also hear in one of our talks, how spatial planning and its impact on rain, how spatial planning can impact the rainwater harvesting potential. Stakeholders' involvement is also one of the important elements in this kind of modeling. But this is not the end of the scope of the water-sensitive urban design models. I mentioned already alternative water sources, and today we will also hear a little bit about optimizing wastewater treatment and reuse, how to optimize different distribution networks, and what needs to be said here is how this impact actually on water supply network. And this is a topic that is not quite frequently addressed in water-sensitive urban design modeling. Last but not least, I would like to also mention urban agriculture, which is also somehow missed in this kind of integrated assessments, as urban agriculture, when practiced on local resources, can also bring many benefits. It can reduce surface runoff. It can serve as a sink of wastewater, so on recovered resources, while producing local food. So with this, I would like to conclude this short introduction to the topic of today. And before we go to our speakers, I would like to mention that this session is being recorded. Your microphones and cameras are disabled due to large number of attendees, and the normal chat function is also disabled. So I kindly invite you to put all your questions in the Q&A section. This is an icon to the low right in the Zoom, and we will do our best to answer your questions during the session. In the end, we will have a Q&A session, and we will address your questions then. So now I would like to invite our first speaker. Our first speaker is Peter Bach. He's an interdisciplinary researcher at EAWAG and a lecturer at ETH Zurich. He specialized in integrated approaches to support planning and design of urban blue-green infrastructure and sustainable future cities. So, Peter, please.
Thank you very much, Natasha. Just going to move this Zoom thing out of the way. So, yeah, thanks for the introduction. Yeah, as she said, my name is Peter Bach. I am based at ETH Zurich and EAWAG in Switzerland, but I did my PhD at Monash in Australia, and we experienced the whole idea of water-sensitive urban design over the last, more than 10 years now. And so, in a way, what I'm presenting today is, call it less technical, because we've done a lot of work in the technical domains across different disciplines, but it's really answering a key question, which is how we then get our science and the multifunctionality that we want to design around blue-green infrastructures, which is the term that I currently use, that or nature-based solutions, how we get that into practice and how we can leverage the space in our urban areas, which is declining quite rapidly due to urbanization and a lot of other challenges. So yeah, I will generally stick to the term blue-green infrastructures because that's what we've been using here in Switzerland, and nature-based solutions equally, sort of on equal footing. But yeah, I'll use them interchangeably. And in my case, I focus really on the urban areas. So it's about these urban systems and how we can adapt cities to the change and challenges of climate change, urbanization, but also declining quality of life. But I think when we think about these kinds of systems or nature and cities, it's nothing new. It's existed for quite a long time. Like we've had first mentions of it in very early publications across different areas of the world. So Heinrich von Thünen's proposals, or Ebenezer Howard's Garden City, or even London's Greenbelt. And there's been a lot of critique over the past decades about the way we've been designing cities and how we need to bring nature back in, because it can provide a lot of different benefits, or ecosystem services, which is the current call it buzzword that really speaks for the use of nature. And so we have seen research emerge across this discipline, and not only in the urban water space, but also urban climate, amenity, urban planning. And so we have different tools, we have different measures, ways we can bring nature back into cities. But rightfully, as Natasha mentioned earlier, this has been done in a very opportunistic, trial and error, ad hoc way. And so when we think about how we can be more strategic about it, we really have to look at the city as a whole. And this is where, from a lot of the research I've been undertaking, you can come to somewhat of a vision of what we call a blue-green city. If we picture how our cities look like today, these big concrete jungles, minimal urban parks, minimal nature, we try to put in things where we can. And we know that this city is going to evolve some 30 to 50 years into the future. Here's just a hypothetical illustration of Zurich. We want to be able to plan our nature strategically so that we can balance a mix of different scales and options. And among these options, if we look at the literature across the different disciplines, we have different types of solutions, from technologies to spatial planning and to policies and regulations. And we have to bear in mind that a good policy or good regulation put in place early enough can also yield very vibrant and green cities. And so you might have a future city which uses things like sprawl control or urban densification or restrictions to zoning in certain areas for large scale improvements, combined with a number of different planning approaches where we change the land uses to restore waterfront zones. We create urban greenways and green spaces. Also at the local scale, things like pocket parks or restoring riparian zones. And then finally, having all these big solutions in place, we then use technologies that we know from the stormwater sector, such as water treatment, harvesting, green roofs, facades, buffer strips, to then complement a lot of these systems. And so this kind of looks like an ideal world, and it sounds great, but the question is, how do we get there? And this is where the power of models can come in, because models are capable of anticipating and allowing us to experiment with potential solutions, understanding what the impacts of putting them in certain locations are going to look like, whether it's for the urban water cycle or whether it's for urban climates or even just the social impacts. So recreation, amenity, physiological, psychological well-being as well. But the problem with modeling and planning support that has been emerging in the literature, I've noticed, despite being evidence-based and providing support for guiding decisions, because we can design these for multiple functions and we can really look at selecting different system types and locations, we're seeing very simplistic current approaches. So it's still been quite monodisciplinary. I think we've seen a lot of progress, which has been great to see how climatologists are using trees to help provide shading, control of wind, or how urban water management is creating these infiltration systems to help protect and restore natural water cycles. But when these disciplines start to look at the topic of multifunctionality, we often see the use of proxy maps, proxy indicators. Often these maps are whatever we can get, whatever's available in terms of the data. And so, that's often very simplistic and doesn't bring in the true dynamism of the processes, whether it's an energy balance, a water cycle, or an ecological balance. And so we then run into problems of how do we actually inform the design and the decision making around these kinds of systems and around the shaping of nature in cities. And then there's the other question, we can go on the other extreme and say, well, we can build a big fancy model of everything that can integrate everything and have all parts interacting with each other. But is that really necessary? Can we actually draw upon first principles and actually provide good enough information that draws from the fundamental knowledge? And this is where I sort of come in with this keyword that I like to call a palette. It's not about bringing in the big AI tool that can solve all our problems, but I think we have enough knowledge from the different disciplines to be able to bring in information that gives us a holistic big picture. And then we can pick and match the models that suit our purposes and the problems that we face in our cities. And so this is where I then ventured a bit outside the water field, because my original core training and core discipline is in the urban water sector. And over the last few years, I've been looking at a number of different aspects in a way to assess multifunctionality. We have urban water management. So knowing that the role of water is actually quite crucial. Green needs blue, because if the vegetation dies in our cities, it's not going to serve many different functions like urban heat mitigation or recreation or biodiversity. And so having the water as an integral part of the whole story is incredibly important. And among that, we also look at aspects like drainage, flooding, water quality, alternative water supply. And so over the last few years, we've been looking at using models like EPA SWIM or EPA NET even to look at the water supply impacts as well. And even just simple water balance modeling or simple flood models to get a spatial sense of what's happening across the urban areas. On the other hand, we also delved into urban heat mitigation, creating cooler environments. It's one thing to know that we can provide irrigated landscapes, or we can put in blue-green infrastructures like tree pits or urban wetlands in our cities, but we don't actually know whether they're going to give us that urban heat mitigation benefits. And so this is where energy balance models, such as, well, the typical ones being ENVIMET or using more detailed CFD models like ANSYS Fluent, could help at a smaller scale. But then there's also models that were built to help assess city scale urban microclimate. And this is what we've also been delving into. And so I tend to use a model called Target, which was developed from a number of different models and put together in the Australian context, but can be used quite readily across the world as well. And so we've been using these kinds of models to explore that aspect of blue-green infrastructures. And really it's about active irrigation. Can we provide irrigation to green spaces, and will they actually reduce daytime air temperatures, especially during heat waves? Can we bring in human thermal comfort and actually assess that and provide some performance indicators around this? Just to make things more interesting and more complicated, there's also the biodiversity aspects. I think one core component of these kinds of systems is the connectivity. With urbanization, we're breaking the connectivity of urban green spaces and landscapes. Now, this is not only bad for us humans, because in a way, because of the car-oriented city, we're creating less safe environments for recreation, for sustainable transport. But that's also having an effect on the urban ecology. And so animals, the diversity and biodiversity is about animals being able to exchange genes. And to do that, they need to be able to migrate across the landscape and exchange, this diversity of genes to be able to be resilient to future challenges. And so we looked at some models in the urban ecology space as well to explore what happens if we start greening the landscape. How can we identify the best locations that will secure an ecological backbone straight through our urban environment and therefore help enhance and protect urban biodiversity? And finally, I mentioned the recreation and the urban livability part a lot. And in relation to a lot of the models that we've been looking at previously, we've also tried to consider this aspect in simple terms in a lot of the modeling work that we do. Now, this is sort of a very diverse palette, as I've mentioned, of different kinds of modeling approaches. And a lot of, this kind of work has been investigated sort of individually in a number of different publications that have come out from the work that my colleagues and I have been doing in the last few years. But where I think the crux or the real value add lies in looking at these many different approaches is supporting practice and actually implementing good solutions. And this is what I'd like to present in some of the projects that I've worked on with a number of architectural studios across Europe. Now, what's interesting about architecture, especially in Switzerland, is they're often the first point of call for these kinds of landscape shaping. And if you can get them to understand the need for nature in cities, you can allow, these ideas to trickle in very early in the planning process, which is crucial if we want to design them strategically and not just place them in opportunistically for the sake of having them. So I picked out 3 studies that I'd like to briefly outline, just to give you an idea of how these models were used in these kinds of contexts. It all began in a competition in Bern, where we had to redesign or redevelop a site that was a former industrial area. And this is really along the river And it's a former industrial gas processing plant, and it became a cultural center in the after that plant got decommissioned. And so there was a competition to redesign it for housing because of the increasing need for housing in the capital city of Switzerland. But in order to ensure that there was ecological value on the site and protecting the existing values, we came in with an initial assessment of urban biodiversity, using our models, as you can see in the bottom right, to understand what are the main passageways throughout the entire region and where does this site sit within that. And we identified a critical zone, which we then allowed, we basically shaped the design of the site around, giving a lot of the space back to nature. To then shape the buildings on the site, we brought in the urban climate models to help figure out what are the current hotspots in the area, surface and air temperatures, and how can we protect the area from getting a lot warmer. And so there's a more detailed video of this particular project that you can look at on my YouTube channel. But what's interesting about this site was then we ended up really designing something that was very rough and gave the space back to nature, and using water as a means to help create this more vibrant landscape. This actually was acknowledged by the city of Bern in the final evaluation of the projects. We didn't quite win the prize, but we definitely confused the jury, and we definitely got some recognition for that. So it was nice to see how already bringing in some of these models to shape the site has led to a decent impact and a good design outcome. Similarly, a few months later, we looked at urban heat issues as well as potential shaping of an area within an existing master plan in Sion, which is known for being very hot. And this is for the first time where we used some of these climate models to then also assess what the architectural designs would result in, what the performance of these designs were. And so in this particular case, we started with the empty existing industrial sites, looked at what an existing master plan could do for urban climates, and then how a site design would then improve that further. And within that, we also brought in more ecological values into the sites and also stressed the importance of water, particularly because it was right next to the Rhone River in the canton of Wallis in Sion. This actually was recognized by the jury, won the first prize, not quite the first rank. Architects are a bit strange in the ratings like that, but it certainly gave us a lot of confidence that these ideas are starting to really gain legs. A final example was a much more extensive design where we were able to shape an entire development from regional assessments. And this is really where we came in with all the models that we had to provide an initial insight of how we're going to place buildings, how we're going to protect areas from flooding, how we're going to place our green spaces. And this is something that recently concluded, but it's something that you'll definitely hear of more in the future, because this was something that we definitely were able to then convince the jury to take it further and actually write the rules for how we're going to design this and shape the area in future. And this was once again also in Switzerland. A number of other ongoing planning narratives that I've been exploring to help figure out how we can introduce these kinds of tools more actively are also currently ongoing, which include redefining a green belt within Luxembourg, also validating an initial design for blue-green infrastructures in Bern, which we've been doing in conjunction with some of our research partners, and a corridor planning that's going to be starting up very soon. So I guess some lessons learned as a modeler, current state assessments, if we're trying to assess it, often the data limitations are very, very serious, and we need to look at it as to how we can use the models to help the decision making. And this, of course, implies that there's going to be challenges with model calibration and validation. And so creative approaches are sometimes needed, given time constraints as well. We need to be able to provide initial quick and dirty assessments to architects so that they can do the initial design and refinements afterwards where possible. And the power of design evaluations allowed us to then show how in relative comparisons we could show that there's confidence in the solutions that are being used and that the architects could experiment with it. Do we integrate? Well, it's not necessary to really link all the models with each other, but to use the models in conjunction to really create a storyline that allows them to then communicate it. And this is where communication is also key. We need to manage expectations and allow that complexity to be presented in a very simple way. Because when we have our model outputs, that often cannot be readily understood by a whole range of disciplines. So key take-home messages from this: multifunctionality, as I've mentioned, is key. It's going to be key in the future because we have space challenges. The discipline and the design is moving towards quantified approaches, and the norm, because it's the norm, modeling is becoming more powerful than ever. And so it provides that evidence base, but we have to approach it from first principles. We don't want to just use simple static approaches. We need that dynamism. And that's what these models can provide, a certain process that is represented visually. So identify the first entry point stakeholder and allow yourself to then engage with them to see what they expect, so that you can then create an outcome with the palette of models, which does not necessarily need to be integrated, but it's really about showing how we can then make a difference from the different disciplines and from the different approaches. So with that, I'd like to thank you for joining. Get in touch if you'd like. There's a number of different contact details that you have. And if you're more interested in some of the work I do and my network as well, I also recently launched a podcast, and you can listen to some of the experiences there. And it doesn't just cover this topic, but also a range of other topics. So with that, thank you very much.
Thank you very much, Peter, for this very interesting talk. So I would like to invite now our next speaker, which is Tony Hargreaves from University of Birmingham. He is also an interdisciplinary researcher developing novel methods of modeling across spatial scales. Tony will present an integrated modeling framework to forecast how regional spatial planning affects the viability of building scale alternative water supply systems. So, Tony, please.
I hope everyone can see that. Hello, yes, I'm Tony Hargreaves, and my presentation is going to be about an integrated modeling framework, which is designed to test spatial planning policies at the city region scale. And so I'm going to present an example of how this framework can be used to test the viability of alternative water supply systems at the building scale, such as rainwater harvesting and greywater recycling. So spatial planning policies affect urban development over the long term. So you can see on the left is the southeast of England. You can see London has a green belt which keeps the city relatively compact, whereas in the Netherlands also they have quite planning policies which keep settlements compact, but they have smaller cities that are more dispersed. And in the Flemish area, you can see that a lot of the development is along the transport networks with lots of small settlements. So you can see there's different policies have different long-term outcomes. So the supply of land affects the density of development depending on the relationship between the demand for floor space and the amount of land available. So if there's relatively little land available for development, such as in city centres, and a lot of activities want to locate there, then you tend to have higher density developments, such as apartment blocks and so on. The middle picture shows the typical housing in the suburbs of England, where most people prefer to live in a house, and then you can some areas that are lower density development in sort of outer city areas. Again, this affects the building types and the type of land cover, how much of the land is permeable, and also the occupancies of the buildings, how many occupants there are and water demands and so on. So this affects the feasibility of the different types of water management systems. So a method was needed to link the regional spatial planning policies to how they would affect development at the local level, kind of neighborhood scale, particularly the buildings. So one way of testing these regional spatial planning policies is to use what's called a land use transport interaction model. So this model will represent how the supply and demand for floor space, and depending on the amount, where firms choose to locate and where the employees of those companies choose to live, that will affect the supply and demand, and therefore the price of the land and the floor space. It also affects the flows on the transport networks, and depending on the capacity of those networks, that will affect the amount of congestion and travel times and so on, which in turn will affect choices of where firms and households choose to locate within the city region. So these models are quite useful for understanding the relationships between different variables and forecasting the relative differences between spatial planning options. And they're quite well established. They've been used for a number of decades now, both in the UK and different countries around the world by planning authorities. The main limitation is that they only provide aggregate outputs per zone. So you divide the study, the region that you're studying into different zones, and the model will provide the total employment by different industrial sectors, the households by different socioeconomic groups, and also the average density. So this is just an example of the model that I'm talking about today in terms of as an example. It has 250 zones, which are mainly focused on the southeast regions of England. It's in London and the surrounding regions. So a novel method was needed on how to convert these total households and the average density for each of these zones into the built form, to be able to test building scale technologies such as the rainwater harvesting, for example. So the method that I devised was to use what I've called tiles, which are for each dwelling type, there are 5 different tiles. So say for example, detached houses, there are 5 tile types ranging from very low density housing to higher density detached. And each of these tiles, the amount of roof space per dwelling will be different, and the size of the plots and the permeability of the plots and so on will be different. So these tiles are designed by analysing English housing survey data, and at the time of doing this research, that survey included data for over 16,000 houses, which have been systematically selected and surveyed. So it's a very representative database, and that provides all the dimensions of the dwellings and the plots themselves. And so these tiles were very useful for interdisciplinary working. So researchers, working on things like energy and water and and waste and so on, could be using the same tiles for designing their systems. But the main point to stress, I think, is that these are not intended to represent layout of the dwellings on the ground as a sort of spatial plan. They're really used as a sort of abstract objects as a kind of spatial accounting system within the model, so that when you add up all of the tiles, each one is 1 hectare, but it can include fractions of tiles. But if you add up all of the tiles to get the total area, and you then get the total number of dwellings of each type, and all of that will match the aggregate outputs for that zone from the regional city region, spatial planning model. So just to give just an example now of how the tiles are used for modeling rainwater harvesting. So here we can see on the y-axis is the water savings, the average water savings for the zone, and the x-axis is the plot density, the density of the dwellings. So we get the regional model provides the population and floor space per zone, and there's also data per zone available on water demands per person and rainfall, so on. And then the tiles provide the dwelling dimensions and the household sizes and how much roof area would be suitable for rainwater harvesting. So for each of those 5 different tiles, for example, for one, let's say for the detached houses, the markers show the water savings for each tile, and then you can fit a function to those points. But these water savings depend partly on, on the water savings per system that would be installed, but also how many dwellings are likely to have the system installed. So as the density increases, the roof area per dwelling will be less. So it's less likely that the system will be cost effective. So these functions, as you can see, are sort of non-linear for the household systems. So just moving on now to just talk about how the dwellings were modelled. They were also modelled using a kind of parametric method. So basically, but from the analysis that I did of the English housing survey data, I found that if you disaggregate dwellings by their type, the area type where they're, and the age band of the dwellings, then you can model the density of each plot using a gamma distribution. You can see that the distributions are slightly skewed to the right, and these distributions for each dwelling type can be calibrated and then used to model the dwellings, and the only input that is then needed is the average density and the calibrated shape parameter. So these distributions are on the same, the x-axis is the same as the water savings on the previous slide. So the water savings can be combined with these distributions to and used to model the water savings for each of the zones, within the city region. So then just move on. This is now an example of how this model was used, and this slide is showing forecasts, because this research was done sort of about 15 years ago now, but we were using the model to forecast over a 30-year period. So the grey bar on these histograms, the other thing to mention is that these histograms are for the water resource zones. These zones are much bigger than the zones of the land use transport model. So they're an aggregation of the outputs of the spatial planning model up to water resource zone scale. So the grey bar shows how many how many of the dwellings that existed in 2001 would still exist in 2031. They're called the existing dwellings. And then the other 3 bars show spatial planning options. And this is for these are new build dwellings over that 30-year period. So each of these options is really addressing a different kind of aims for spatial planning policy, because when it comes to regional spatial planning, there's often a lot of, we could say, different opinions amongst planners and about what the priorities should be, and not just planners but the government as well. So compaction is really addressing the aims to improve the environment by reducing the amount of travel and the amount of energy demands in buildings and so on. So that's really building higher density within existing urban boundaries. The trend is generally based on the spatial planning policies of the local authorities at the time of doing the research, which tends to be for development to be more compact than what the existing development that was built in the past, but it still would include building on some new greenfield sites in certain areas around the existing settlements. The market-led option is really addressing the sort of need to increase the supply of, well, to satisfy the demand for housing and make housing more affordable by building more houses in the locations where people want to live and where the economy is growing the strongest, for example. And these would tend to be at lower density than the other two options. So then, just give an example of for what rainwater harvesting. This on the left, you can see that the dwellings increase, and this shows the water savings per water resource. And first thing, if you could see perhaps on the either side of London, you can see that the increase in existing dwellings was fairly similar for two of the zones. If you then compare it to the map on the right, you can see that the water savings would be less in the east because the rainfall is much less in the eastern region than it is in to the west. So so the water savings per dwelling vary over the study area because of the rainfall. Also, the water savings per dwelling would be greater for the market-led option because that tends to be lower density, and therefore the houses have more roof area per dwelling, and it would be correspondingly less for the compaction option. So this next one is a similar comparison for the grey water recycling. One thing you can see here is that the biggest savings would be for the compaction option, because most of those new dwellings would be apartment blocks, which would be suitable for communal systems, which would tend to be more cost effective than having individual systems per household. And also, if you compare look at London, for example, you can see for existing dwellings, the water savings will be very little. That's mainly because of based on the assumptions made for testing these options, because London tends to have small households and less water demands per person. Then for most of the existing houses in London, it wouldn't really be cost effective to retrofit them with grey water recycling systems. So finally, just conclusions. This integrated modelling framework achieves a difficult challenge of linking the regional scale modelling to built form at the building scale. It manages to achieve that by not attempting to represent how they'd actually be built on the ground, but to use this more abstract method of modelling just the buildings as in an abstract way without attempting to model their physical layout in different areas, because that's sufficient for modelling these water systems at the building scale. So it would be useful, this type of model would be useful for optioneering on how spatial planning options would affect the longer term future potential of sustainable technologies, such as the extent that they could reduce demands on conventional water networks. And some of the outputs could therefore be useful for planning the water management for water sensitive cities. And finally, I think it would be very useful, I think, for water companies to have this type of model, because then they could engage with planning authorities using similar models or even a joint model on scenario analysis to better coordinate spatial planning and things, for example, building regulations as well for the local building scale, and policy support such as subsidies and so on, to get the best combination of spatial planning and resilience for water management in urban areas. So this is a list of some publications showing, I'm just in italics, their relevance to this presentation, and I think that's concludes. So yeah, okay, thank you very much. That's great. Okay.
Thank you very much, Tony, for this interesting presentation.
Yeah.
Before we move on to our third and last presenter, I would like to kindly remind you to put your questions if you have any. And also, I would like to inform you that you will receive these slides as PDFs after the webinar. So now we go to our third presenter, and this is David Martinez. He is a PhD candidate at the Catalan Institute for Water Research, ICRA, and at the University of Girona. So David, please.
Hello, everyone. I am David Martinez. I am a PhD candidate from the University of Girona. Thank you very much for inviting me to this webinar. And today I'm going to talk about the optimal design of water use networks in cities. So I'm going to present the decision support tool, development and testing. So first of all, water use cannot wait any longer. So especially in the Mediterranean areas, water scarcity and drought cause an urgent need for water use. So we can see in this diagram on the right side of this slide that this the current state of water reserves in Catalonia. So we can see that we are now about 26% of capacity of our reserves, and 2 years before was about 85%. So this is a huge problem. So obviously the design of reclaimed water networks, we all know that it's an expensive problem and very complex for technical operators. So can you imagine an optimal planning of water reuse networks, which means serve maximum amount of water with minimum costs? So now it's the time, and we present a novel decision support system to automatically design these optimal water use networks that we call ReWattNet. So there is an active discussion of whether to apply centralized or decentralized approaches to water reuse problems. So in this case, we focus our research on centralized approach, although we maybe will take into account the centralized approaches in future works. Then to begin with, first it's necessary to define these scenarios in order to use the tool. So the tool only needs two user inputs that are the identifier of the city and the city cadastral files. So identifier can be only the city name, and the cadastral files represent the land uses of the city. So with only these inputs and the customizable default values, we can generate these designs. So these customizable default values are basically the reused water consumptions per use and per day, and also the construction costs, which includes pipes, bulbs, and tanks. So inside of the uses we are taking into account for water reuse, the tool considers three main categories: the economic operations, public, and domestic. Inside the economic operations, we have the commercial applications, such as toilet flushing and other industrial consumptions. We have also modeled the public use that will be basically for urban equipment and public garden irrigation. And then we have also domestic use, with mainly toilet flushing and also private garden irrigation. So we have an example here of a city cadastral data file. So we can see all the land plots, and we have marked some areas that are potential destinations for water reuse. This combined to other open data sources such as the OpenStreetMap API or also elevation information that in cities in Spain is specific of the Instituto Geográfico Nacional, that is the Geographical National Institute. We can then generate these reclaimed water networks. So first of all, we generate the initial graph. We get this from the initial city street graph, the cadastral files, and the elevation database. So we can see in this diagram the raw street city here in gray. Then we have the cadastral files and other additional information. And this is all aggregated to what we call the initial graph. It's the larger below picture. So we got all this information, and then we link our water source, that is usually a water tank or the wastewater treatment plant with a proper treatment for the water to be reused. And then we serve this water to potential destination nodes. To do so, we apply several algorithms, and we get some relevant output indicators. So we can see that we are basing all of our algorithms in graph theory, so it's very important for us. We apply also clusterization algorithms in the case of large cities. If we want to make a planning of a large city with the whole city, let's say, maybe a clustering solution is more appropriate. Then we have several routing algorithms that we use to design the reclaimed water network. So basically, we are trying to connect our source node with all the destinations, and to minimize costs, we do so with minimal trees, and specifically with the Melchor algorithm. Then we have two algorithms that we have implemented. There is the first of one is the diameter selection algorithms. This algorithm selects an optimal diameter for each pipe of the reclaimed water network, and based obviously on the destination consumptions. So in order to minimize the construction costs. And then we have a specific case of use that is the limited budget algorithm, that it's an alternative algorithm, an iterative one, that tries to maximize the water that we can serve, the reclaimed water, with a limited budget. Obviously not all the times we have all the money in the world to build this kind of network, so we work usually with limited budgets, and this is a really interesting application of it. So the algorithm basically evaluates the addition of potential consumption nodes, considering their consumption and their cost of adding them to the network. So it's a candidate evaluation, let's say, and we consider the potential destinations that consumes the more and costs us the less to adding on our network, depending on where is the source or water or initial water tank, let's say. So then we get some interesting output indicators. Normally we get graph files of the generated network results. We have also very rich visualizations on map, interactive also. And in the case of numerical indicators, we also get the total water saved, the network length, and the water saved, and obviously the disaggregated and total network construction costs. So moving on to a case study, we applied these algorithms and this tool to the city of Girona. We applied the tool considering the entire city with all reclaimed water uses and 5 clusters. And we have also considered all reclaimed water uses with limited budgets. But first of all, we did a validation study in order to check if the consumptions of our model were accurate or not. So we carried out this validation study to calibrate the model with, let's say, the information that our model predicts and the actual consumption for the city of Girona, as we have the data from the competent authorities. So this table shows us the results. So if we look at the global numbers, we see that we only have a 6% of error between these figures, so it's quite good. And it's true that we have quite overconsumption in the case of public uses. Our model predicts more consumption than it should. And we think that is because of our detection of green areas, because it includes the public garden irrigation. And we think that not all these areas are being irrigated in practice. So this is the cause of this overconsumption, but the overall numbers are quite good. So moving on to the results of this case study, we can see that considering the entire city with all reclaimed uses, the total demand ascends up to 7,000 cubic meters, and with a total length of 155 kilometers. We can see here in the right the image of this generated network. So it's 5 clusters. Each cluster is identified in a different color. And we have at the bottom of the gray lines represent the city streets, the initial graph, let's say. And then, well, in each cluster, we place in an optimal placement of water tank. And then by gravity, it's served within all the cluster. So the total construction costs of this case ascends up to 16 million euros. And one other interesting thing is that the position of these water tanks in each cluster matches very well the real locations of the city water distribution network. So we think our model is quite good in the optimal positioning of these water tanks. So moving on to the limited budget case, the algorithm maximizes the water set with a limited budget. So it's quite interesting to see that at 30% of all the water demand, the reclaimed water demand of the city can be covered with only 2 million euros budget, which is about 12% of the original cost for covering all the reclaimed water demand. So compared with current practice that is based on a manual approach, our tool increases the water served by a factor of 3 in this case of limited budgets. So what we consider a manual approach? We consider a manual approach to simply connect our closer destinations within our source point of water until our budget runs out. That will be the most currently used technique for the industry. So we can see here in the right what this network will look like. So it's like a form of minimal tree, and we can see in red the result generated by the tool over all the city streets and the original source of the water. So moving on to another case study, we have also tested the tool with El Prat de Llobregat, which is another Catalan city. And in this case, we applied the ReWattNet in the entire city, considering all the reclaimed water uses and with limited budgets. But we have used another version of the algorithm. We have improved the limited budget algorithm. We adapted some things on the profit function and some implementation issues that clearly improved our results. And then we have tried another novel algorithm that is still a prototype, that will be the limited budget resilient, that not only tries to minimize at maximum the cost with maximizing the water served, but it tries to prioritize resilience, providing more mesh networks that will be more realistic in some cases. So to do that we present a novel measure that is the availability, that is a measure originally from the Technical University of Delft. And we use that for performance evaluation of resilience in water distribution networks. We can define this availability of a water distribution network as the probability that all the water demand nodes in a network are served by or connected at least with a water tank, and we're having a failure probability of our pipes. So this gives a very good framework for performance evaluation of resilience in water networks. We have here a comparison between a tree network and a meshed network. The limited budget algorithm generates a tree network, let's say, and the limited budget resilience generates more meshed networks. So in case of failures, it's more or less likely that, that a demand point may be disconnected or unavailable to get the water. So this new algorithm of limited budget with all the improvements is more accurate and fast. And with the same budget, we can provide 20% more water compared to the original one. So we have here a comparison table, and we can see that the water saved passes to from 50% to 73%, and also in less execution time. So we have improved that. And here in the right, we have an image of what this network looks like with the same format as the other image. And finally, the limited budget resilient algorithm, as I said before, tries to find independent routes, and with this technique improves resilience. So we can see in the table that obviously our water saved decreases a bit because the other one was the more optimal one without considering resilience. So we have a 20% more or less decrease on water saved, but the measure of network availability increases to a 76%. And what does it really mean? Well, to having that network availability means that in the 76% of cases, the network is not affected if 1% of all pipes fail simultaneously. So this will be the vision. And obviously, because the limited budget does not consider resilience, it is a very low value in this case. So to end with the presentation, I presented the RoWattNet tool that is used for an optimal design of water use networks. So with very few inputs, we can automate the design of reclaimed water networks. We also use clustering and routing algorithms that are based on graph theory. We have presented novel algorithms such as the diameter selection that selects the optimal diameter for each pipe based on the diameter demands, on the destination demands, sorry. We have the limited budget algorithm that maximizes the water served and minimizes the construction costs. We have also an improved version that is more accurate and fast. And we presented the limited budget resilient algorithm that creates more meshed and resilient network designs. So we have here also the article that we have recently published on the NPG Clean Water Journal. So all the information is detailed there. And that's all. Thank you very much for your attention.
Thank you very much, David. Now it's time for our session, question and answers. So we have here, I would like to start with one question, and it is for Peter, but possibly Tony can answer it as well. So the question is as follows. In addition to being responsible for developing mitigations to rising urban temperatures, the Chief Heat Officer of the City of LA is also tasked with identifying inequities in the impact of extreme heat events. Are any of these models compatible with the inclusion of demographic information to investigate how improvements can protect particularly vulnerable neighborhoods? Sorry, Peter, your microphone is not working well. Maybe Tony, if you have an answer, maybe you can start.
Okay.
And
yeah, okay. Well, first point I'd make is that in the presentation I showed, I had the slide showing what I call the tiles, which were just shown schematically, really. But each of those includes information about the amount of land that would be covered by paving, for example, how much would be permeable, such as gardens, and how much would be roof space. So that can give some indication of the amount of heat island effect. Also, at different densities, the proportion of land occupied by roads and paths and other paved surfaces tends to increase with density, and there's a sort of function I've produced in one of my papers that shows that, but that can be, information can be produced relatively easily. The other thing which relates to vulnerabilities of particular socioeconomic groups, the spatial planning models for the city region, they include different household types, and they show how, for example, lower income household types will tend to locate in the areas where the land values are lower because the housing is cheaper in those areas. They often tend to be in the less attractive parts of the city. Therefore you can map, based on the planning policy, what is the likely distribution of households of different types within the city over the, say, the next 30 to 50 years, depending on the forecast period. The only limitation with these models is that they're not really able to model the location choices of retired people and the elderly, because they're no longer really affected by economic growth and travel to work and these sorts of factors that affect location choice. So in that sense, they need to be input based on demographic projections from other sources. So okay, I think over to you, Peter. Yeah.
Thank you, Peter.
Does it work now?
Yes.
Okay, good. Not sure what happened there. Yeah, so I mean, it's definitely an interesting question. I think I in particular haven't looked at inequalities or inequities in the work that I've been doing, but a lot of the models I've been using are GIS based, so spatial based. And yeah, the idea is, I think, if you can model these kinds of phenomena, then being able to then intersect them in GIS, which is the outputs that these models also provide, to look at where these hotspots align with places of inequities is something that I think you can do to take the work further. One of the tools that I developed myself, which looked at access to green space, I'm trying to develop further to incorporate more demographic information, but I think it's a matter of time before we get to these kinds of indicators that identify inequities. What's certainly interesting, though, is in the location choice, and Tony, you touched upon this as well. I think it's an interesting relationship to see how locations or ideal locations for these kinds of blue-green infrastructures sort of align with biodiversity needs, urban heat needs, urban water management needs. And so it's definitely a research question for the future, but I think initial, suspicions I get is we often talk about the luxury effect in urban heat, where the richer neighborhoods tend to have more green because people like to have more more greenery in gardens that are fancy, whereas the poorer neighborhoods may have less. So we might actually be planning for, if we plan for heat, we might be targeting some of these areas as priority zones, but this is just, I guess, a hypothesis for now, which you can certainly see sometimes pop up in the literature. But the fact that it's all spatial, I think, allows us to then intersect it with these kinds of data sets, and perhaps also socioeconomic models that touch upon these kinds of issues.
Thank you both. So the short answer is it's possible. Okay, so let's get to one more question for David. And the question is, how much scalable is the tool that you presented? Can the tool be applied to any European city, and how much effort it takes to run it on a particular case study?
Okay, so this is a very good question. And we think that the tool is quite scalable. So we tried with Girona and other several cases study and works pretty well. So I think also with work with bigger cities, maybe would take more time to run, but it will also work. And now how it's the tool made, it's direct for any city in Spain. And it can be applied to any city worldwide and European cities also. But it will be necessary to change a bit the preprocessing of the data because it is adapted on the cadastre files from the Spanish government. So each country has its own format. So it will be to adapt a little bit the preprocessing of the data and how we get the elevation, because we get the elevation from the National Institute of Spain, but we also have other providers that we can use. So we can use practically the tool anywhere, and we only need these cadastre files and the preprocessing of it in the format that the tool needs. And the only other thing we need is the name of the city, because the city street is obtained through the OpenStreetMaps, which is available worldwide. So will take not much effort to run it on a particular case study. As I said, for a Spanish city will be direct, and for other cities it will be this small adjustment, but it will be very feasible.
Thank you very much, David. We have no open question. So I would like to ask Ulf if we have time maybe for one more question from me.
That we certainly have, Natasha. Please go ahead.
Okay, well, I would like to continue, David, with you. And the question is, how did you determine the potential points for the destinations of water use? Were there any particular algorithm or was it by hand?
Well, we have an algorithm in order to predict that. In fact, what we do is from the cadastre files, we get the land uses of every, let's say, parcel. And then we have from several research works that we have reviewed carefully, we get some equations and formulations. So depending on the extension of this land use, we get some consumption that related to this, let's say. So with all of this information, we can select the decided uses we want to consider, depending on the treatment that we have for the water with our treatment plan, let's say. And then the tool with all this information is able to get a model of the amount of water needed by each destination, and then we only have to design the network to serve it, let's say.
Thank you very much. I have plenty of other questions, but I think it's time to slowly close. And I would like to really thank the three presenters. I think we had really nice presentations, very informative, very much novel, and I give the words to Ulf.
Thank you, Natasha. Just a few final words, 1 minute, and then we can go home. So thank you, everybody. Once again, just as Natasha said, including Natasha this time, for a great show. I want to remind you that I mentioned it in the introduction that we will have another webinar from the MIA Specialist Group, and that will be on May 19 at 10 o'clock Central European Summertime. And that will be based on the newly published scientific and technical report by the task group that just concluded their work. So very, very hot stuff and very, very interesting stuff. And also just to remind you that if you have, those of you that are listening in on the webinar, if you have an idea on a webinar for half an hour, 1 hour, or so on, that you feel that you would like to bring forward and set up with maybe 1 or 2 or 3 speakers and so on, then don't hesitate to contact the management committee of our specialist group, and we will do what we can to make it happen for you. With that, just want to thank you all, and remember to follow the specialist group on our websites and LinkedIn and Twitter to keep updated of what is happening. Okay, thank you very much, wherever you are. Bye-bye.
Bye-bye. Thank you.